So, in class we talked about parallel plate capacitors, right, which look like this. And then I said you could also have spherical capacitors, right, which look like this. Or you could think about cylindrical capacitors that look like this. Oftentimes, when you actually draw a cylinder, you actually draw it like this as, the straight on view, the top view. So when you see a picture like that, you need to actually know if you're dealing with a sphere or a cylinder. But in general, when we look at these, we define like inner radius as A, outer radius as B. Same thing here. But big idea is if we want to know the capacitance, then it's Q over the potential difference between the two plates, okay? They're the two conductors. So for spherical and cylindrical capacitors, the idea is we calculate the potential between the conductors, right? So here's a positive charge, here's a negative charge. You know there's going to be an electric field from there to there, right? And obviously, it would have been nice if I'd used different colors, but you got it, okay? So that electric field that goes from positive to negative, right? You can figure out the form of that, right? Using Gauss's law, okay? And if you know the E field in a certain region, then you can calculate the potential difference in that region and we're going to go from B to A. Remember, we start at infinity and go back in. So you'll go B to A. The other thing to remember here actually is that delta V is really an absolute value, delta V, right? Capacitance is a positive charge, or a positive number, right? So we wouldn't have any sign here. All that matters is the absolute value of the potential difference. So even though I write this, super correctly with that negative and going from B to A, when you're actually doing these problems, you don't have to be as careful with the negatives and the B's and A's and A versus A to B. But I'm trying to be careful here just to keep you consistent and continually seeing the correct way of thinking through it. The other thing to notice just while we're looking is the electric field. So you remember the electric field is 0 outside the capacitor, and then inside it has some value. In this case, for parallel plate capacitors, the value is sigma over epsilon naught. It's going to be the same thing here. E equals 0 outside, E equals 0 inside, 0 and 0. And that's, pretty easily seen by Gauss's law, right? The charge enclosed, inside here, that's pretty clear, right? Because there's no charge inside there. But when you do the Gaussian surface out here, you see it's a plus Q and a minus Q. So that's how you get no electric field, because there's no net charge on a capacitor. All right, let's just do the derivation. So the first thing we need to do is figure out what the electric field is inside, in between A and B, right? So again, we're figuring out delta V, right, from B to A. So we need to actually know the electric field in that region, okay? And we know that it's going to look like that. And we say, it's a sphere. My goodness. The area of a sphere is 4 pi r squared. My quench is just plus Q. Okay. By the way, if you happen to have your negative Q on the inside, that's totally fine. Again, we're going to just be looking at the magnitude of the electric field. And the magnitude of the electric field from plus Q or minus Q wouldn't matter. Okay, so hopefully at this point you are not surprised to see that, right? That's KQ over R squared. All right, so hopefully you kind of see what's coming, right? You should be having sort of intuition at this point that if you have an electric field that's an inverse square, that your potential should be just 1 over R, right? So let's be a little bit careful about making sure we take into account the B and the A. So I'm going to write delta V negative E dot dr from B to A. Okay, negative Q over 4 pi epsilon naught R squared dr from B to A. Let's take out those guys. So there's a negative out here. Integral of R squared, 1 over R squared dr is negative 1 over R. And we're going to evaluate that from B to A. Okay, let's keep going. So now we get a little plus, cute. All right, 4 pi epsilon naught. Now, 1 over A minus 1 over B. Okay, that's delta V. So are we done? No, we're looking for the value of the capacitance. So we're going to say Q over V. So it's Q over Q, and then I'll bring the stuff up here, 4 pi epsilon naught, and then this down here is 1 over A minus 1 over B, okay? Just take a second and see what I just did there. This is just 1 over delta V, okay? So do you see what happens? The Q's go away, and then we can do some nice sort of math here. So we go 4 pi epsilon naught. If we're going to combine, right, 1 over A minus 1 over B, we can say that's AB, B minus A. All right, so if that's on the bottom, then B minus A is here, and AB is here. So what's kind of nice here is, by the way, B is greater than A, so this is actually a positive number. So if you actually are careful with your B's and A's and your negatives, it will actually work out to be the correct positive number. So this is lovely. Why? Because this is all geometric factors, okay? So you are not expected to know this capacitance. So epsilon naught A over D for the capacitance for a parallel plate capacitor is something that you should have off the top of your head. But the capacitance for other distributions or other setups, you shouldn't know. But they absolutely are well within their right to ask you to derive it, just like I did. All right, so let's do a cylindrical capacitor now. So what you see I drew already is a cylindrical capacitor. And the red dotted thing is my Gaussian surface that I'm going to use to figure out my electric field. Oops, that's quank. My electric field in between A and B, right? So this is A less than R less than B, because again, outside and inside, right? So R less than A and R greater than B equals 0 because quank is 0, right? Because this guy has a negative Q, this guy has a positive Q. Okay, so we are really, really trying to focus on what's happening in between there. All right, so let's do this. E times what is the area of our Gaussian surface? It is 2 pi RL. Okay, so that, of course, L is whatever that is. Our quank is going to just be what the plus Q that's inside there. So Q over epsilon naught. So here we are. Our electric field, and hopefully this looks pretty familiar to you, right? It goes as 1 over R. Do you remember that? Hopefully, yay. Okay, so that electric field is going to be what we use when we're calculating our potential difference. So let's plug that in. We get Q over 2 pi epsilon naught LR dr. Let's keep going. Let's pull that stuff out. 2 pi epsilon naught L. All of that is just lovely and constant. Okay, now it gets interesting. What is the integral of 1 over r dr? And hopefully you remember that it is natural log. So when I write natural log, so ln to me as a physicist, I often just say log. I'll try very hard to say natural log for you, but I will probably slip up at some point because when I see ln, I think log. So now we're going to evaluate that from b to a. All right, negative q over 2 pi epsilon naught L log a minus log b. Okay, you probably remember some fun tricks that you can use for subtracting logs. So let's go. Remember that it is log a over b, right? Log a minus log b is log a over b. And then this is another thing that they like to do when they simplify. Do you remember also that the negative of a log is, right, log of the inverse? So we can write q over 2 pi epsilon naught L log b over a. Okay, so that is our delta v. So let's bring that to the next slide. All right, so now is the easy part, actually. C equals q over v. Right, even though you spent so much time calculating delta v, don't forget to actually answer the question. So C is q over q, and then that 2 pi epsilon naught L, which is on the bottom here, will go on top, and then that's log b minus a. Our q's cancel, and there it is, ladies and gentlemen. The capacitance for a cylindrical capacitor. Okay, so check it out. Only geometric factors. Awesome. B is greater than A, so that's looking good. We're not having like a log of a number less than 1, because that would be a negative number, and then your capacitance would be negative. But you know, if that happens, you know, so be it. It probably still works out if you just take absolute values at some point, but it's probably good to just do it the right way first. Admittedly, I haven't done it the wrong way and done the whole calculation with that switched, but feel free to try it and let me know if you get the same answer. Okay, I just wanted to throw one more thing in here, and that's the idea of putting capacitors in series and parallel. And we'll do way more of this with the circuits, but right now at least you can understand where these formulas come from, and you've probably seen these formulas somewhere. So before we derive them, let me just maybe define these for you. Series is when capacitors look like that. Parallel is when capacitors look like that. So when we look at circuits, these wires here, wires, everywhere along a wire is the same potential, okay? Now, when we look at a capacitor and I say, okay, let's say this is, I'm at the potential 3 volts here, I'm at 0 volts here because the potential difference across this is 3 volts. That's how that works. Okay, so when we write things like Q equals CV, that's the V we're talking about. We're saying this capacitor has a potential difference of 3 volts across it. That means that this wire has a potential that is 3 volts higher than this wire. Okay, so that's sort of what you need to understand before we actually try to derive it. Okay, all right, so capacitors in parallel look like this. So we have 2 capacitors, let's call them C1 and C2. So they have like different values, like 3 microfarads or 6 microfarads, that kind of thing. And what we want to do is we want to say, can I replace this setup with 1 capacitor of equivalent capacitance? And so there are formulas for that. We did this a little bit with springs. When we talked about springs, we said, okay, we've got 2 springs in series or parallel. Can I replace it with 1 sort of K equivalent? And that's exactly the same thing that's happening here, okay? So what do we know? We know that, let's change some colors here. We know that some charge is going to go in to this junction, and it'll split, and you'll get a Q1 and a minus Q1, and you'll get a Q2 and a minus Q2, okay? And we know that the relationship, before we talk about the relationship, the whole idea in parallel means they have the same voltage across them, right? So when I talked about this wire having 3 volts and this wire having 0, this is that same wire, okay? So that's that side, and actually let me just say, okay, well, this guy is at a different potential, and so that blue could be 3 volts and that green could be 0 volts. That's what we mean by that. And again, that is, and you can see when you look at these capacitors that they each have, the voltage across the first capacitor is the same as the voltage across the second capacitor. Okay, but what do we know? We know, oh, by the way, that voltage across the first capacitor and the voltage across the second capacitor, that would be, let's keep our fun color coding things here, that would be the same thing that we would look at when we're looking at that equivalent part, right? Okay, so hopefully that helps. So V. So that's that V. Okay, so we know that the total Q, right? I'm having fun with these colors, so let's keep going. The total Q that comes into this junction splits between the capacitor 1 and capacitor 2. So hopefully you can be easily convinced that the Q total is Q1 plus Q2, okay? And then over here, that equivalent capacitance just has the Q total, okay? So can we write an equation? We know that Q total is C equivalent times the V total. And this is C1 times V1, and that's C2 times V2, right? Because Q equals CV. So that's how I wrote this next equation. But, V1, V2, and V are all the same. So that's how I get my C equivalent is C1 plus C2 when they are in parallel. Okay? This obviously goes for all, like if I have more than 2 capacitors in parallel. Okay, awesome. That's parallel. Okay, so let's take a look at capacitors in series now. I'm going to do this same little color coding thing that I did before. just came up with it on the fly right here while I was doing this, but I think it might be really useful visually when we start working on circuits. So let's just keep doing that. So if this side is at a certain potential, that's going to be the same guys there. All the way over here, that's going to be over here because we're trying to replace C1 and C2, figure out what combination will replace that. But there's a wire in between, and that is not the same potential as either the blue or the green. So when we talk about the potential across capacitors, this, sorry, let me grab black. This is the total V, right? But there's a potential drop here and a potential drop here. If you want to put numbers to it, if I have 3 volts and 0, right? So maybe, so that's 3 and that's 0. This is somewhere in between. And that depends on the values of these capacitance. If they were equal capacitances, that's right, then it would be like 1.5 volts, right? Because they're kind of like stepping down. You have to go from 3 down to 0. But the point is that V1 is not equal to V2 now, necessarily, right? And it's definitely, but they definitely are not equal to V total. The relationship there is V total is V1 plus V2. Do you see that? V1 is 3 volts minus whatever this is, 1.5, and then V2 is 1.5 minus 0. So they add up to the total. So now, when we say Q equals CV, what if I write V equals Q over C? Well, you might say, well, what about Q? What about Q1 and Q2? Well, if I have a certain charge here, and I have then I have the negative of that charge there. So because there's this amount of charge going in here and no other path for it to go, we know that the charges on the plates have to be equal, okay? So when we write Q over, and then that would be, of course, the same charge here. C equivalent, sorry, I've just staying in red apparently. V1 is going to be Q over C1, V2 is Q over C2. Our Q's cancel and you get this relationship. So this is for series capacitors. There you go.